Hi guys, welcome to your first actual lesson with stats. Hopefully you guys enjoyed your spring break, even though you probably couldn't go anywhere. Hopefully it was relaxing and you feel refreshed and ready to go. We're going to try to do these notes. We're only going to do half of them today and then you'll get the other half on Wednesday. So nothing too crazy. We're starting chapter 5, which is normal distributions. So if you ever hear about things on a bell-shaped curve, that's what we're doing right now. So if you hear people like grading on a bell-shaped curve, that means that they're forcing people into the middle. So a bell-shaped curve is perfectly symmetrical, and the highest point is right in the middle, which isn't typical, but you can force that to happen, okay? In order to be a normal distribution, it has to be continuous, which means there's no gaps, okay? You guys know what that word means. And the graph has to be normal, meaning it has to be even on both sides. Okay, it can't be lopsided, kind of like the one I just drew, not lopsided. So if you just look at a curve on a graph, if it's going to be a normal curve, the mean, the median, and the mode are all equal. So let's think about what that means. The mean is your average, so it has to be in the middle. Okay, the middle of everything, the center. The median is the center. So if the mean and the median are equal, that means that the center is exactly the same for both mean and median. Mode is the most. So the highest point on the graph has to be the same as the middle point and as the average between the two. So all of that together means it has to be perfectly symmetrical. So your highest point at the top, okay, is your mode, but it is also the center, so there's an equal number of numbers on one side and an equal number of numbers on the other side, and it's exactly balanced on each side, making your mean, median, and mode all that peak of the curve. Okay, it's bell-shaped and symmetric about the mean, so it's symmetric about that middle point in the center. Okay, the area under the curve is equal to 1, and we'll do a lot more with this later, but just know that's coming. So the total area is equal to 1. The curve approaches but never touches the x-axis, so it's like an asymptote, okay? And it extends from the mean, so it can't drop below that x-axis. And then within one standard deviation of the mean are your inflection points, and we're going to focus on these inflection points a lot today. Remember, standard deviation talks about how spread out your data is, so the more spread out, the fatter your curve, so the wider your curve, and then we're going to be able to estimate what the standard deviation is, so how spread out it is, based on the inflection points. Okay, so we're going to talk about that today. Inflection points are the place in the curve when it stops curving up and starts curving down. So it's kind of tricky, but you have to think about it. Clearly right now this is curving up, okay? At some point it has to switch so that it can start curving down, okay? And then eventually it starts curving down. So our goal with inflection points are to find that place where it stops curving up and starts curving down. If you think about it, if it's going to change directions and it's not very obvious, it's not like a sharp turn, it's not like you're going up and then coming back down, it's a curve, it's smooth. So we kind of have to look for the flat space in between where it's clearly curving up and where it starts to clearly curve down. Okay, those are going to be where your inflection points are. So somewhere in this flat space in between is when it's going to be an inflection point. So probably directly in the middle where it looks flat is where that inflection point is going to be. Okay, your mean, your median, and your mode are all directly in the middle. So mu is in the middle, and so is your mean, so is your mode and your median. Your inflection point right here is going to be symmetrical with the inflection point on the other side. So they're going to be two inflection points on your bell-shaped curve. Okay? Each of those represents your standard deviation. So that's baby sigma. So one standard deviation to the left and one standard deviation to the right are your inflection points, or those places where it stops curving up and starts curving down, and vice versa. Okay? So we're looking at 4 completely different curves here, but they are all symmetric about their mean. Okay, these are all bell-shaped curves. They just look different because they're spread out and they start in different places. Okay, so if we start by looking at the green one, The green one is about as normal as it gets. Okay, so it's coming up, and then eventually it has to turn back around. You know that your mean is in the middle, so this is my mu. Okay, so the inflection points where it stops curving up and starts curving down are probably closer to about here and here. Okay, again, it's going to be in that flat area. It's clearly curving up here, and it's clearly curving down up there. So somewhere in between those two places is where it's going to have to switch directions. Again, if you pick it over here, it's going to be symmetrical, so over here is going to be the same place. Okay, and those are going to be where you are, where your standard deviations are. Okay, let's look at the red one. On the red one, it's a little bit more spread out. So your inflection point, so here's your mean in the middle, mu. Your inflection points are probably a little bit further out. So they're probably here at 1 and -1 because it's more spread out. So the fatter your curve, the wider your curve, the more spread out it is, the further your inflection points are away from your mean. Okay. If they are here at 1 and -1, that means that your standard deviation, your baby sigma, is 1. On average, your data is, each individual point is about 1 away from the mean. Okay, so you've got that going for you. And let's look at the blue one. The blue one is super close together, like it moves really fast. When it moves that quickly, your inflection points are going to be a lot closer to your top. Okay, because it's got to be going up for the most part and then start to curve back down. When that happens, because it's not very spread out, your inflection points are going to be closer to the top because your standard deviation is smaller. Okay, the distance away from the center has to be further away because your inflection points and your standard deviation is not as spread out. If you look at the yellow one, it's super spread out. So if it's really fat and taking a long time to reach its peak and come back down, that means that those inflection points are going to be a lot further out because the data is more spread out. Okay, so those inflection points are a little bit easier to see actually because you can tell here it's curving up and then all of a sudden it starts to curve back down. So I would say these inflection points are all the way out at -3 and 3. Making that standard deviation 3, which is pretty big, okay? It's really spread out. On average, if your data point is 3 away from the mean on a bell-shaped curve, that's super spread out, okay? So the mean is your line of symmetry or the center of the curve, so we talked about that. And the standard deviation, as always, is how spread out it is, but in this case, when you're just given a curve, it's how far away your center is from your inflection point, okay? So if we're looking at these, which curve has the greatest mean? That's not the highest point necessarily. It's the one that has it centered furthest to the right. Okay, so graph C has the highest mean because its center is closer, further to the right. Like if B would just be shifted over here, it would have the bigger mean. Okay, it's not the highest. It's whichever one has the center further over. Okay, so our mean there is 12, so graph C would have the biggest mean. Now, standard deviation is how spread out it is. So if you're just looking and you just want to know which one has the biggest standard deviation, it's whichever graph is slowest or fattest or more spread out. So A is definitely our more spread out one here. So A is going to have our greater standard deviation. Okay, hopefully that makes sense. You don't have to do anything on your own. So if we are looking at this and we want to know the mean and the standard deviation, the mean, again, is going to be directly in the center. So if we look here, our center is at 100. So the mean, mu, is 100. And then to find your standard deviation, you have to know where your inflection points are. So this is pretty basically spread out. It's not super fast or super slow, so it's not going to be really far out to the edges or close to the top. It's going to be pretty much in the center. So wherever it stops curving up and starts curving back down, it's going to be where your inflection points are. So I would say my inflection points are here and here. Symmetric, okay? So to find your standard deviation, it's how far your inflection points are away from your mean. I know this is kind of hard to read. It's a fuzzy graph. But our center was at 100, and now over here, my inflection point is at 115. So the distance between 100 and 115 is 15. So that makes my standard deviation 15. Okay, so it's how far away. Again, you could go this direction too. Between 100 and 85 is 15. So each inflection point is 15 away from the center or your mean, which means your standard deviation, your baby sigma, is 15. Okay. Okay, I'll give you your homework. I'll post it separately. And that's going to be due by tomorrow at midnight. If you have any questions, just contact me on Schoology or on Zoom. I hope you guys are doing well. Miss you all. Bye, guys.